Now I'm writing Lagrange's equation, d dt dl dq dot is equal to dl dq. This is what I'm doing. And I'm doing it for the A0 and for the A. Okay? So I compute. I want you to notice that this object here does not depend on A0 dot. This is an important observation. And it's going to give us trouble, serious trouble. But that's what it is. That's how physics is. And you compute. So here I computed for you all the derivatives. And I'm getting delta E equal to 0. That's the codifferential. And d dt equal to delta B. I get two of Maxwell's equations. I need two more. Well, one of them is completely trivial because B is dA. So I take one more derivative and I get 0. And now what I do is I have to take, I'm going to get this one. And this one I get from the previous one, from this equation here, by taking a differential. Because I don't have variables B, I have variables A, right? So I have to take a D. Remember, I'm doing something which is not totally orthodox. But that's what I'm doing. Now, if you want to see this like engineers see it, then you have to pass to vector fields. So the sharp and the flat operators and the star operators are Riemannian. Sharp raising indices, flat going down indices, and star is the Hodge operator. And if you do this, you actually get the equations in vacuum. So if you are curious, this is what the curl is, and this is what the divergence is, right? In terms of differential calculus. Okay, now we can choose without loss of generality A0 is equal to 0. You don't see it here, but in the non-abelian case you will. But we can still kill it. And there is a standard argument that you find in engineering books, like Jackson's book. If I have an A0 prime and an A prime that satisfy Maxwell equation, I want a phi such that A is equal to A prime plus d phi, leaves the equations unchanged, and A0 is 0. Well, how do I do it? Well, the equations are second order because I have Lagrange's equations. So the dots really mean ddt's. So I write this down, right? I know that B prime is equal to B. Just look at it, right? I have to take the D. Nothing happens, right? So the only condition that I really have to impose is that E is equal to E prime. I write everything down. And indeed, I find that d phi prime is equal to this. So sufficient for me is to choose this. Hence, I can choose A0 to be 0 if I so want that phi dot is equal to this A0 prime. And I'm done. If you want to see the four-dimensional representation that you see in all the books, it's extremely easy again. I go to a Lorentzian manifold, and I'm putting a connection one form. Of course, this is so simple that I don't really need to say that, because it's real valued, right? The group is the circle, but here it is, right? This is the curvature, and you get the standard form df equal to 0 and delta f equal to 0. Okay, now, you say, well, now do Hamiltonian. You can't. You are in real trouble. The Legendre transformation for L is not bijective, it's degenerate. It doesn't depend on a dot. If it doesn't depend on a dot, you cannot pass from Lagrangian to Hamiltonian. And this is unfortunately endemic. It is true for essentially all relativistic field theories. You have to come to grips with this. This is why I wanted to do this exercise. So now what I'm going to do is I'm going to do the Hamiltonian thing anyway, but I cannot do it like I do it in mechanics, because the Legendre transformation is no good. Okay, so let's keep going. So I'm doing a completely different game now. So I'm taking the configuration variable to be just one forms. I cut it down. It's not as big as in the Lagrangian case. And the Hamiltonian is just the electromagnetic energy this time is E squared plus B squared. Now E is simply a matter of sign convention. It's minus y, because these are the conjugate variables. And I write Hamilton's equation. Right? dq dt is dh dp, and dp dt is minus dh dq. Right? This is what I'm writing. So I get two of the equations, right? And I apply d to the first equation. Again, I'm doing something that is not quite kosher, right? But I get it. And of course, the relation b equal to dA gives me that dB equal to 0. I miss one equation. How do I get it? From where does it come from? I need a fourth one. Well, much, much more subtle. the equation delta equal to 0 is due to a conservation law. So there is the gauge group, which in this case is just Fm, acts on the form simply by translating by a differential of a function on the fiber. So now, if you are a symplectic geometer, you know exactly what to do. You have a cotangent bundle, you have an action on the configuration space, you compute the momentum map. So you compute it. And the momentum map turns out to be the codifferential of y. Now, if you set that this to be equal to 0, you get delta equal to 0, you got your fourth equation. Right? Now, let me make a few remarks. In the Hamiltonian formulation, we have used only on the configuration variable a, whereas in the Lagrangian situation, I used a0 and a. In addition to that, the variable a0 can be set to be equal to 0 without any effect on the equations, even in the Lagrangian case. But I have used the a0 dot. Yeah, I cannot just get rid of it. Okay. In addition to that, we have used the conservation law and have applied d to one of the equations. What have I really done geometrically? I have performed symplectic reduction secretly. I'm not going to go through this here with you, but this is really what I have done. I have taken the inverse image of 0, and I have divided by the group. Dividing by the group means I have to take d of the variable. I really have performed symplectic reduction. If I perform symplectic reduction and I want to write the symplectic form, or rather the Poisson bracket, then I do get the Pauli-Born-Infeld bracket, which I have no time to show you. So you get f dot equal to fh, where the bracket f with h is the Pauli-Born-Infeld bracket in 1931. Okay, now in the Euler-Lagrange equation, delta E equal to 0 was obtained from the variation of the Lagrangian relative to a0, which is exactly the variable whose dot is not appearing in the equation. Right? It's quite, it's not as clean as you may think. Now, my first intermediate goal is to do this for Yang-Mills. Okay? So let me try to do this very quickly. We are all geometers here, so I can go extremely fast through this, but you do need to know what isomorphisms I need, and you do need to know my notation, right? So I have to go through this. So I have a principal bundle. All my bundles are right. Phi is the action. Letters like psi, eta, zeta are elements in my Lie algebra of the structure group. And my infinitesimal generator is denoted by psi index p. Here is the definition, just to make sure that you know what I'm talking about. And the vertical subspace are the vectors tangent to the fiber, so they are the values of the infinitesimal generators at points. Now I can build the adjoint vector bundle, right? I just take the bundle that is associated. Here is the action. This is my convention on the action. It is a right action. I have to be very careful. You see, when you do mathematical physics, you know, theorems like there exist are not very good. You have to compute, you have to show equations, you have to be very precise in what you're doing. Right and left plays an important role in continuum mechanics. One is convective representation on the left, and one is spatial representation or Eulerian representation on the right. Since I'm doing fluids, I better stick on the right. I have to be very careful on which side I act. Okay, so here is my notation. I mean, I don't know if it is standard notation or not, but I have to use it. So this omega k bar are the equivariant horizontal one forms. And by equivariance, I mean right equivariance. Here it is. That's why there is a g minus 1 here, because the action is on the right. Okay? Now, there is an isomorphism. Every body who's equivariant and horizontal induces a bundle-valued form on the base, as we know. And I just wrote the explicit isomorphism. These corner brackets index g means that I have taken the g orbit. I have taken the equivalence class in the quotient. And there is an inverse, which I need. And here it is. I wrote it explicitly down. So if I take a point and vectors here, I take my form, which is bundle valued. I project everybody down. And then I have to use an isomorphism between the fiber and the Lie algebra, which works because the action is free. And this g is the unique one that connects P to Q, because Q and P must be in the same fiber. Now, specifically, if I'm with functions, these are equivariant functions, and these are sections of the adjoint bundle, okay? So I wrote the isomorphism again here, the same way. And the principal connection, just to make sure that you know what conventions I'm using, this is the equivariance condition, and of course, the vertical space is the Lie algebra. The connection space is an affine space with the underlying vector space, the horizontal equivariant 1 forms, the vector space underlying it. So I have a horizontal splitting with a horizontal space that behaves good relative to the action. My notation is HP and VP. Okay. The covariant exterior derivative is the usual one. I simply take the exterior derivative and pick up the horizontal part. And the curvature is just the covariant derivative relative to A. I need 3 equations later. I need the Cartan structure equations. Here they are. So when I write AU, AV, I literally mean what I write. In other words, I compute A on a vector. It's a Lie algebra element, another Lie algebra element, and I take the bracket. And I have the Bianchi identity, which I'm going to use, and the funny other identity, which is the second covariant derivative, which is the bracket of the curvature with the function that is Lie algebra valued. Now, by general nonsense, A induces an affine connection on the adjoint bundle, an affine connection on the coadjoint bundle. I need the covariant derivative on the coadjoint bundle, which is this dual, which I denote this way. And I have the codifferential. Now I have to explain just a little bit what the codifferential is, because I need to tell you what metrics I'm using, right? So the metrics I'm using are the following. I take an invariant inner product on the Lie algebra. This induces a bundle metric on the adjoint bundle. Here it is. This is an element in the bundle. This is another one. And I just take the representatives. Everything is okay because this is all independent on choices of representatives. Now, the Riemannian metric induces a bundle metric on any form bundle that you care. And now I denote by G gamma the bundle metric of K forms with values in the adjoint bundle. And concretely, this is given in the following way. I write alpha x, alpha a, fa, beta x, fa, beta a, fa. Fa is a basis in the fiber. So these are 1 forms, right? These are forms whatever degree I want. I take the metric that induced on the bundle, and then I contract with the inner product in the Lie algebra. So this is my metric, G gamma. And then, of course, the A is just and delta A are adjoint, as we know from elementary Riemannian geometry. This is all I needed to tell you. And once I have this, I have the Kaluza-Klein metric, which is the sum of the 2 metrics on the base and in the fibers. Okay. Now, I forget that. My automorphism groups is denoted by OT, and these are diffeomorphisms which are equivariant. For each automorphism, there is a unique diffeomorphism that drops to the base. I call this by phi bar. The Lie algebra of OT P consists of G invariant vector fields on P. Careful, its left Lie bracket is denoted like this, which is the negative of the usual bracket that we have. I don't know if you know this. We in geometry don't care, but in mechanics this is important because it changes the sign of the equations. The Lie bracket that we have in geometry, just to vector field, x on y on f minus y on x, right, is the right Lie algebra bracket of the diffeomorphism group. It is not the left Lie algebra bracket. I want to use standard formulas, so I compute left Lie algebras, but if I do that, I have to change the sign in front of the bracket. So this is the Jacobi Lie bracket because Jacobi introduced it. The bracket was not Lie for reasons because of mechanics. And by L is just a left Lie bracket, the usual left Lie bracket that we teach our students. Okay, so for every u in such a vector field, this guy is dropping, and I have a pi relatedness between u and u dot. And if I put an index mu, it simply means that whatever drops down conserves the volume. This is what I wrote here. The gauge group are all those automorphisms for which the dropped down diffeomorphism is the identity. This is a normal subgroup, and it is isomorphic to equivariant functions from P and G where equivariance is relative to conjugations. Right? There are 3 adds. Right? Conjugation, there is an add, there is an add, and there is an add. Right? It's conjugation, the adjoint action, and the adjoint action of the Lie algebra on itself. 2 big letters, 1 big letter, 2 little letters. Right? So that's why I sing them to you. Okay, so there is an isomorph. The isomorphism is given in this fashion. So what do I do? From the gauge group, I go to these functions. How do I do it? Well, it is the unique group element such that phi of p is connected to p by that group element. That is phi hat of p. That is the function. This is the explicit isomorphism. So I have a bunch of isomorphisms here. The gauge group, equivariant function relative to the adjoint action, and sections of the adjoint bundle. I miss one isomorphism, this one. I'm telling you what it is. How do you do it? If I give you a function, I compute its value. It's an element in the Lie algebra. Take its infinitesimal generator and compute it at the same point. So you have f of p, at that p is a Lie algebra element. Take its infinitesimal generator and evaluate that vector field at the same point p. That's why there are two p's here. And the transformation law of the connection is given in this fashion. Okay, now if it's trivial, there are various things that happen to be semi-direct products, but I don't think I'm going to get there. So I'm going to skip this. I don't have time. Now, if it is not trivial, I have this sequence, and these isomorphisms that are semi-direct products fail. You have to be very careful if it's not, if the bundle is not trivial. And the example is, as usual, given by the Hopf vibration. Here is an example. The antipodal map is not reached by anything if you integrate this sequence to the formal Lie groups underlying it. Okay, one more thing I need, and then I can get going. I need duality. I need to tell you what is my cotangent bundle at every single step. So here is how I do it. So if I look at the cotangent bundle of the automorphism of P, these are one-form densities, but not honest-to-God ones. They are covering a diffeomorphism phi, right? They are not just densities, they are not sections. They are sections covering a diffeomorphism phi. So I have to tell you how I pair it with a vector field covering a diffeomorphism phi. This is the tangent space to the automorphism group. This can be all made very precise with correct topologies. Okay? So what I do is this is a function on C infinity P. This does not depend on the fiber variables. Therefore, it drops to the base. On the base, I have a volume form. I integrate. That's the number. That is a weak duality pairing. Okay. Therefore, the dual of the Lie algebra of this group of automorphisms turns out to be the space of right invariant, not equivariant, invariant one forms on the manifold P. Okay? That's why the G is down and there is no bar on that. Now, when I do it for the gauge group, it's a bit more complicated. So here is what I do. I have to give you two vectors and I have to tell you what the metric is. So clearly I'm going to integrate something relative to the volume and I'm going to use this gamma. But how do I do it? I take just any principal connection out of my pocket and then I recall the isomorphism between the horizontal equivariant ones and the adjoint bundle K-forms. So these are vertical and the pairing does not depend on A because A of U phi is given in this fashion where the sigma was exactly this isomorphism that I told you before. I showed you three isomorphisms, one of them being with the gauge Lie algebra. So the point is that, and then I lift it, and then I can integrate. The point is that I have a duality pairing here also. Good. Now let's get to work. So this time I'm going to repeat what I did before. These are the field equations. So here is my Lagrangian, is the tangent bundle of equivariant functions on P relative to the adjoint action, the space of connections. And is defined exactly as before. I use the same letters. Now where E is a bundle-valued form on the base, and this is what is called the electric part of the Yang-Mills field, if you wish. Right? And then there is a magnetic part of this, which is a two-form, on the base bundle valued, right? This B to get here used to be horizontal equivariant. and this E was horizontal equivariant 1 form. But they are equivalent to bundle valued forms on the base. And this is how I want to work with them. So here they are. And the norm is whatever norm is associated to whatever form I need, 1 or 2 or 3 or whatever. Right? I put 1 and 2 because I work in 3 dimensions. But so I do the same computation as before. Okay, the computation is a bit more complicated, but it's not serious. And I get delta E is equal to 0, and I get this equation. Notice here I have a term that didn't used to be before. E is exactly the same form as before, except that the exterior differential now is a covariant differential relative to a connection. And I get other 2 equations. This is the Bianchi identity, right? So this comes automatic. And I apply the covariant derivative to one of the equations in order to get the B variable, because I don't have B as a variable. My variable is A, is the connection. It's not the curvature. So again, something is funny, but it's the same type of phenomenon. So now I can tell you I'm going to eliminate this A0. I don't want to see it. I can do it. So if I take A0 prime and A prime that satisfy Yang-Mills, I want a phi such that A equals phi star A prime, leaves the equation unchanged, but has A equal to 0. So I want the same equation without these 2 terms. I just don't want them, exactly as I had before. And it is perfectly possible, even though it's non-abelian, because all I have to do is I have to know that B equal to phi prime B prime is automatic because phi is a gauge transformation. So my only condition is that the electric part is the same. All I have to do is I'm going to write index T to show you where I have, honest to God, time dependence. I just write the condition, I compute it, I replace it, and then I'm faced with a derivative here. Well, I sit down and compute this derivative using the transformation law. Okay, this is a little lemma. It's not totally obvious, but it's a little lemma. So I'm telling you that if you take the derivative of this, which has this formula, this is what you're getting. Okay, I plug it in, and by the time I'm finished, I get that all of this is equivalent to this condition. Sufficient condition is to have this in order to get that the electric part is the same. I can choose exactly as before A0 to be 0, provided that phi dot phi minus 1 is equal to something which has Lie algebraic significance. Notice that this is the Eulerian velocity, right? It's exactly the Eulerian velocity of my medium. And I eliminated A0. There is a covariant formulation. Let me not go through it. You recognize, you have exactly the same thing. The curvature, the covariant derivative and the covariant co-derivative of the curvature is 0. Again, as before, I have a problem with the Legendre transformation. I cannot do it. I have to do the Hamiltonian situation separately. So I repeat the game. This time I have, again, only A and Y. I don't have A0s as before. I have the full energy of the field. I use the same notation, E equal to minus Y. I compute exactly as before. I get 3 equations. I get 2 equations, and the Bianchi identity comes for free. Right? Previously it was D squared is 0. This time is Bianchi. I need the 4th equation. I do exactly as before. I have an action, the gauge group. The gauge group acts by pull back, and I cotangent lift it. I compute the momentum map. I find the momentum map. Here it is. The cotangent bound of the connection is going into the dual of the Lie algebra of the group that acts, and it is given by the covariant derivative of this put in the right place. This is this isomorphic sigma. And what I'm getting is that delta A E is equal to 0. Again, I have performed symplectic reduction by hand because it was very simple. So far, so good. We have field equation. Now I need particles. I have to put all of this together. Okay, so what do I do now? I have a connection. I have, again, an equivariant function. My Yang-Mills field is given by the electric part and the magnetic part. And I'm considering the right invariant Lagrangian L given by the kinetic energy. Here it is, relative to the metric, and on the Lie algebra part, right? These are all Lie algebra elements. Well, L is invariant, therefore it induces a Lagrangian on the quotient. Now, if we were sitting in an abstract geometry class, the situation is over. I have given you a manifold, I have given you a free proper action, you take the quotient, okay, go ahead and do it. If you talk to a physicist or an engineer, if you tell him that, that person is going to walk out. You haven't given him anything. I want equations. I can't tell you there is a quotient out there and you compute. Compute, please, right? Do it, okay? You can do it. Use the Atiyah sequence. So what this means is that there is an isomorphism of bundles over M, which is the quotient, of this quotient, abstract quotient, by the Whitney sum of the tangent bundle and the adjoint bundle of P. And this isomorphism, which is connection dependent, is the following. Well, here it's completely clear. If I take a class of a vector field, all I do is I project the one of its representatives to the base. And this is the independent. What do I put on the adjoint bundle? Very simple. I look at the base. I compute the connection on the vector. I know I have somebody in P, somebody in the Lie algebra. I'm allowed to take the equivalence class. Now I'm in the adjoint bundle. That's what I did here. This is correct. It's independent on all choices. And this is an isomorphism of vector bundles. So what do I need to do? I need to take the equations that are here on TP. I need to drop them, and I need to follow them by psi A. And now I have to write the equations down. So let's do it. It's quite instructive. So here, the Lagrangian drops. This is not too difficult. Here is the Lagrangian that drops here and then pushed forward by this psi A. Is the kinetic energy on the base and something in the Lie algebra. Okay? So far, so good. Now what I need to do, I have to perform what is called Lagrangian reduction. That really means that I have to push forward by psi A. So here is the theorem. Okay? This you have to compute. This is not something you can do in an afternoon. I guarantee you that. It's not difficult, but you're going to have to work. So the statement is the following. By now you got it. Red color are theorems, blue color are definitions, right? So P of t is a solution of the Euler-Lagrange equations for L up in Tp, if and only if the base and what happens in the adjoint bundle, psi of t, are solution of what is called the Lagrange-Poincaré equations. I'm going to come back to this. So here they are. Let's look at their structure. Look what's happening. What do you see in the first equation? You see various derivatives. There is a time derivative. This is a covariant derivative relative to the Levi-Civita connection G. That's where there is a G up, right? Now imagine that this term is not there. And that everything is trivial. Then what I have here, V is x dot. So what I have here, I have dl dq minus d dt dl dq dot equal to 0. These are Lagrange's equations, right? So this is Lagrange's equations on the base, made covariant with a coupling term that depends on the curvature. Okay? What do you see here? Again, there is a covariant derivative here on the coadjoint bundle, but just pretend it's a ddt. What I have here is d dt dl dx is equal to minus s star c dl dx. These are what is called today the Euler-Poincaré equations. I'm going to tell you more about them. Or, if you are familiar with Hamiltonian formulations, they're the so-called Lie-Poisson equations. Okay? Again, everything is here made covariant, so I have to tell you what I'm doing. These derivatives are very simple. They're fiber derivatives. V is in the fiber, X is in the fiber of the bundle. So I know exactly what I mean. Anybody can take a fiber derivative. This one is trickier. I'm not going to go into details. You need to compute, it's a partial covariant derivatives of L relative to two connections. The Levi-Civita connection on the base and the principal connection A on P. This term does make sense, but you have to understand it in terms of connections. Okay, so if you want functional derivatives, then you go to duals. So I denote like physicists delta L, delta over delta, whatever, as opposed to partial as I had before, right? And this guy now is going to be in the dual of this, which I identify with a space, right? Which is exactly what I'm doing here, you see. Here, I erase the star, I write it down, and it starts looking better. There are Lie brackets here, it's a Lie bracket in the fiber. This raises the index relative to the metric. Okay, now I compute it. So here are the computations, explicitly to compute. There is a little L bar. I want to isolate the L bar because this is the standard kinetic energy of the particle, 1/2 mv squared, right? Like in high school. So the conclusion is that the trajectory x of t and the charge q of t are solutions of what is called the non-relativistic Wang equations. So here they are. This is charge conservation. And here is F equal to ma. Here is ma, you see it? Ma is equal to an explicit expression of F. What is this F? It's Lorentz force law, like we learned in high school, V cross B, right? So let's really push this so that you recognize it completely. Let me take the simplest possible case. P is equal to M cross S1. Then the adjoint boundary is just M cross R. The Lagrangian is completely breaks up. All these isomorphisms become identities, right? My Tm plus add P is just Tm cross R, right? Very simple. My Lagrangian is kinetic energy on the base and in the fiber. Very, very easy. And I write down the Euler-Poincaré equations, and I get conservation of charge. And F, M, this is Ma, equal to electromagnetic force, right? Now, if dimension M is equal to 3, and if I write this as vectors, then I really get back to high school. This is the Lorentz force law, right? There it is, written covariantly. Okay, now, let me see where I am with the time. Okay, I have to tell you something. In 1901, Poincaré wrote a paper which is 1.5 pages long. There is an explanation of this paper by excellent explanation by Charles-Michel Marle that is 37 pages long. Okay, that's how much ahead was Poincaré. Okay, Poincaré writes. I'm sorry, I don't have the citation. It's absolutely amazing. He doesn't quote anybody, doesn't give any motivation, but he says in the introduction, I have come across these equations of mechanics that I think are so interesting that I have to tell you about them. That's it. Finished. That's what Poincaré says. And then in 1.5 pages, he does it. What I'm going to show you is a generalization of what Poincaré has done because I need it. I need other parameters, etc. So what Poincaré has done is exactly what Lie has done on the Hamiltonian side. It's completely parallel. And these people never talk to each other. It's absolutely astounding. It's exactly the same thing from the point of view of mechanics. Lie did the Hamiltonian side with the Lie-Poisson bracket, which then in the 60s became Kirillov constant Souriau bracket. This is the only thing Lie did not know. Lie did not know symplectic geometry, but he did know Poisson geometry. It's amazing how far he went. It is the formula for the bracket is explicitly written with a number on a certain page of his second volume of Kontinuierliche Transformationsgruppen. There is no question that he didn't know it. In fact, Lie knew that the dual of the Lie algebra is more important than the Lie algebra. Lie came from mechanics. He was not an algebraist by any stretch of the imagination. Right? And that is exactly why he did it. Poincaré did exactly the same thing on the Lagrangian side. Exactly. If there would have been a mechanician, he would have instantly asked this and this, because this is natural. Anyway, so the situation is the following. Let me go very quickly. I have a representation, and I take the semi-direct product. My actions are on the right. There are 16 ways to define, which are isomorphic, the semi-direct product. This is the one that I need. And then, of course, the action, the induced action of the infinitesimal generator is written like this here. Xi acts on V. It's on the right. Everything is on the right. Here is the coadjoint action because I need it. Now there is this mysterious diamond operation. Here it is. This is pairing in G. So I give you an element in V, an element in V star, and I'm supposed to produce for you somebody in G star in the dual of the Lie algebra. This is what you do. If you know symplectic geometry, you know exactly what I'm talking about. Is the momentum map of the lifted action. So if you want to generalize this to nonlinear things, this is the momentum map. And this has been done. But let's stick to algebra at this point. This is just this operation. Okay. Now, what do you do when you have when you do continuum mechanics? You usually have a system which depends on parameters. Example, you have the rigid body that moves around a fixed point which is not the origin, which is not the center of mass. What are the parameters? The parameter is the length. It's actually the momentum between the fixed point and the center of mass, right? How about fluids? If I give you compressible fluids, what are the parameters? It's the initial density, the material density. So physical systems depend on parameters. And my parameters are V, rather V star. So what I'm given to you is I give you a configuration manifold, think rigid body SO3, and some other parameters. Anyway, what I have here is like SO3, and here is some other parameter. The rigid body doesn't have this. These are my field equations that they do have, and there are other parameters in addition to that to V star, like the momentum or the initial density. I fix A0 in V star. Think of rho 0 in fluids, the initial density. So I freeze A0 and I have a Lagrangian, and now I want to write Lagrange's equations down. Okay? Now, right invariance of L determines a function G cross TQ on V star in this fashion. You can always go back and forth between them. Now I give you a curve in G of t, and I give you a curve psi of t in the following way. I take the derivative of a curve in the group, I bring it back to the identity on the right because I'm doing fluids. If I were to do rigid body, I had to do it on the left. And I define AT as the unique solution of this equation. But I know what the solution is. This is dragged along by the flow. Dragged along by the flow means by the action. The action on the lifted to the contragradient representation. Okay, so here is the theorem. Hamilton's variation principle holds for variation of G and Q with fixed endpoints. GQ and G of t, Q of t satisfies the Euler-Lagrange equation LA0 on G cross Q. This needs no proof. This is super classical mechanics, right? Knows no to Lagrange. He has it explicitly in his book. However, now comes Poincaré, or an extension of Poincaré. The constraint variational principle holds L psi of t, Q, Q dot, and A. Notice there is here A0 is fixed. Here it's moving. It's not the same thing. Okay? Holds on G cross Q upon using variations of what form? The delta xi has to be of this form. There must be some curve eta such that delta xi is the d eta dt minus xi eta. Delta A is equal to minus A eta. Eta vanishes at the endpoints and delta Q vanishes at the endpoints. I come back to this in a second. And here was variational principle. Here is equation. Here is variational principle. Now come the equations. This is equivalent to the following system of Euler-Poincaré equations with parameters coupled with the Euler-Lagrange equations. So here they are, d dt del L del xi minus eta xi del L del xi plus this term. This is coming due to the semi-direct product. And here are the standard Lagrange equation on Q. Now, this theorem is relatively easy to prove, and the only thing that I have to explain to you, where does this come from? This is rather mysterious. This is, in fact, the content of the theorem. So imagine that there is no Q. I am purely on TG. That's all I have. Purely on TG. Forget this parameter. But I have these other parameters, V star, right? When I have a rigid body, there is a length. I'm sorry, it's there, right? I give you a fluid, I have to give you a density. I can't ignore it. Okay. So the question is, you see, when you do variational calculus, you take this point, you take another point, you take all the possible curves that connect this point to this point. And therefore, the variations of the curve at these endpoints are 0. This is how you do variational calculus. The question now is the following, right? When I have all these curves, I parameterize them, call them epsilon. So this is q of t, call q in this epsilon of t. Take dd epsilon of that, right? That's a tangent vector at the point q index epsilon of t, right? But this is in the group, in the tangent space of the group. Bring it back to the identity. And now I'm in the Lie algebra. Do I get everybody or not? No. That's the point. I don't get everybody. I get only those for which there exists an eta such that. That's what you have to prove. And if you think this has to do with the Gauss lemma, it does. Those of you who are versed in Riemannian geometry recognize the Gauss lemma. This is dd epsilon ddt. This is ddt dd epsilon. Come on. And this is the bracket, right? It is the Gauss lemma. Okay? Fine. So if I were to do fluids, let me show very, very quickly how this goes. My group is the diffeomorphist group. My parameters are functions. I have no extra parameters q. The duals by L2 pairing, I identify them. I mean, if I were to talk to an analyst, he would shoot me doing such things, right? But, you know, formally I can do it. Here is my action. My action here is as a density. This is a Jacobian, the Jacobian of this diffeomorphism. And here is just changing of variables. So this changes as functions. This changes as densities, right? Okay. And my Lagrangian is kinetic minus potential. Physics gives me potential, right? If I don't have potential energy, I have no physics. It's pure geometry. And now I compute these equations. I literally compute, forget these. I literally compute these equations, right? Plus, I don't need to forget that there are also such equations for the parameters. They are dragged along by the flow. And this is what you get. This is exactly what you get. This is the first equation, and they are dragged along by the flow. And this is thermodynamics. This is physics. I have to tell you who P is. P is rho squared dE d rho, depending on rho and entropy. This is definition of pressure using thermodynamics. So that's where physics comes in. Now, if I do ideal, I can do Yang-Mills ideal fluid, right? There I would take the automorphism. My Q now, there is a Q, are these equivariant functions and the connections. My parameters remain, if I take the duals, the density and the entropy, right? My configuration space here, variable is phi. I have my A0 and A, exactly as before. My action is exactly as I did before, except that here now I'm on the base, where phi bar is induced on the base by phi. The Lagrangian for Yang-Mills field fluid is simply, here it is, for the particle, minus potential and the field, right? And my notation is exactly as before. This U bracket is what drops down to the base. Here is M. So here you see that they're pi related. Okay, so roughly speaking, so that you see, the Lagrangian looks like this. Particles minus internal energy plus Lagrangian for the Yang-Mills field. Right? This is what you see in physics. Okay, so now you look for invariance. This is Noether religion, right? You look for invariance, look for conserved quantities, and physics will tell you something immediately. That's correct, and this geometry. So this is what I'm doing. I'm looking for invariance. Here it is invariant by the automorphisms. Therefore, I can take the quotient. Here is the space after I took the quotient, and I compute the Lagrangian. And here it is. Now I compute a long computation. This is long. And I get the following theorem. Psi A0 and A in the automorphism equivariant function and connections is a solution of the Euler-Lagrange equations up if and only if U A0 and A, which are given in this fashion. Here is the Eulerian velocity and here are the parameters on a tangent bundle, right, is a solution of the Euler-Yang-Mills equation. Now look, this is exactly as you would expect. Here is the fluid, and there is some electromagnetism here that couples through the curvature. Here is advection of conservation of mass, advection. Here is conservation of entropy, advection. And I have equation for Q, the electric field, the magnetic field, time dependent, and the constraints that come from Yang-Mills. Here they are. Delta E is equal to minus Q, delta E is equal to B. Where, I can tell you where everybody who is, P is given by physics through thermodynamics. The electric field is exactly given as you have seen it before. The magnetic field is the covariant derivative. But then, of course, I can interpret it as bundle valued when I want. And when I don't want, I use the other way, right? Look here, both of them appear. Some of them are script, and some of them are not, like here. You see, depends how I want to write the equations. But of course, they are the same. These are isomorphic. I know how to pass from one to the other. And here is the charge. Okay? Here it is given as an equivariant function. Here it is as a section of the adjoint bundle, if it's Latin or script. Now, if I take P to be M cross S1, I have come full circle with the equation with which I began, Euler-Maxwell. I've come exactly where I started. Okay, now, if I forget this is incompressible. Now, what do you do on the Hamiltonian side? There is another theory, of course. On the Hamiltonian side, there is, this is Lie Poisson, this is Lie, this is not Poincaré. I give you a Hamiltonian function on T star G, T star Q, and V star. Notice that the parameters in the Lagrangian case and in the Hamiltonian case are the same. They're always V star. The spaces on which they act are different. These are cotangent bundles. The previous ones were tangent bundles. But the parameters are always the same. This is why the theories are different. Okay? So you have the same situation. You have the contragradient representation and everything else. So now here is the theorem that says that alpha t in the cotangent bundle and mu of t I bring with the right translation to the dual of the Lie algebra. These are these curves. The following things are equivalent. These objects here, alpha t, qp, and pt, satisfy Hamilton's equation on this cotangent bundle if and only if the following system of Lie Poisson equation with parameter coupled with Hamilton's equations hold here. So here are the Lie Poisson equation. This is the coadjoint action on the semi-direct product, which has to be spelled out. I will show it to you in a second. Explicitly written here, the two components. And here are classical Hamilton equation on T star Q. S is the semi-direct product, then I take its dual, and it has a Poisson structure. The Poisson structure is degenerate because it is on the dual of a Lie algebra. This is where Poisson geometry comes in, and here you see it, the Poisson structure on the semi-direct product. How do you interpret this? This is pairing between the dual and the Lie algebra. These are functional derivatives. So f is defined on G star. So the functional derivative is in G star star, so it's in G. So therefore I can take the bracket. Here this is the action of this Lie algebra element on this element in V. So this element is in the vector space V, which I pair with the element in V star. It makes sense. This is a number. And this is just a canonical bracket. Okay, so this is how you find the Euler-Yang-Mills equation in the Hamiltonian case, and you do and you do exactly as I did before. You simply write down the energy and you compute the bracket. You write F dot equal to FH, like Hamilton did, and you compute, and you are going to get the equations. It's a longer computation. Again, you are going to have to trouble. Again, you have to worry about the fourth equations. I want to show you the end result. The end result is here. all of these are solutions of Hamilton's equations for the Hamiltonian, if and only if these variables, m, a, and y, satisfy these equations, where we use the same notation as before, except that here v and q are given in terms of m. M is rho v, morally speaking. Okay? And I have conservation of j, which gives me delta a equal to minus q. This equation is missing. There should be here another equation, a constraint equation from Maxwell's equations, analog, the Yang-Mills analog of Maxwell. And here it is. It's coming from here. Again, I have performed reduction secretly, which I haven't shown you completely, honestly. I have shown you parts of the reduction process. I want you to notice that there are funny things here. Look here. Who are the variables? M, A, Y. There is a problem. There is Q here. What has happened? Well, let's start this way. First of all, here is the Poisson bracket, the non-canonical Poisson bracket. So you write F dot equal to Fh, where you take H, the Hamiltonian that I showed you before, and you identify coefficients, and these equations come out after 3-4 pages of computations. But that's not difficult. Okay? The question is, what has happened? There is a lot. I want to make these comments, and then I'm done. The equation for V and Q are the components of a single equation. The equation is for M. M, in fact, determines everything. Look here. If I know M, I know U. But this U, I don't care about this U. But if I know this capital U, I know Q. I apply the connection to rho U. And then I take this U and I drop it to the base. I get V and Q out of M. So there is one equation that has split in two. Okay. Conversely, if I give you rho V and Q, the fluid momentum can be constructed. Here is the explicit formula. Here is the one that I gave you explicitly. How do you construct it? U is given horizontally lift V and put this charge part to it. And then you have this identity. So the Lie-Poisson equation for M is equivalent to two equations. The equation for V and the equation for Q. That is exactly the Kaluza-Klein approach. That is exactly what Kaluza-Klein have done. Out of one equation, they produce two, and the other way around. Okay, the Q equation looks like an advection equation. I want to show you this. You know, it looks like this. So you say, well, wait a moment. It's exactly like the mass equation. Rho dot plus rho v is equal to 0, div rho v. So what's the difference? The difference is that there is an A here. This is not the usual divergence. This is the covariant divergence. So you say, well, so who cares? Well, you care very much. Why? Because A is time dependent. A is a variable. You see what I mean? You take, this is not advection. It's not dragged along by the flow by any stretch of the imagination, because at every instant of time, my A is a different A. It has dynamics. Right? There it is. Right? You have seen it before. It's all here. Look. This is the dynamic variable. It's here. It's the dynamic variable. It even has a conjugate variable. You see? Now, is this important? This is crucial. It's absolutely crucial. Does this appear in other parts of physics? Absolutely it appears. It appears in places where we geometers, to my own shame, didn't know. It appears in liquid crystals. In the screen on which we are using, in the TV screen. These appear in the Erringen equation for liquid crystals. If you look at Erringen, who was a civil engineer, this is a real sad story. Liquid crystals are very important. We mathematicians did nothing about it. Okay? The physicists did nothing about it. Okay? It was the engineers who came. The engineers asked, to our own shame, what are the PDEs? What is the geometric formulation? How do you understand the phenomenon from a geometric point of view? Ericsson Leslie. Leslie was an engineer. Ericsson actually sat in a math department, but he's really not a mathematician. He's an engineer. Ericsson was a civil engineer at Princeton. Was running around Princeton, I tell you, because I talk to people, asking mathematicians, telling you, please tell me what I'm doing. And no one told him he's working with connections. Can you imagine this? In the land of Yang and Mills. This is what he did. More complicated. Ericsson equations have a variable which is called the rise, and that variable is, in fact, is a connection. Is it important? Absolutely it's important, because once you understand the geometric structure, what do you do next? You try to do analysis. But the geometric structure tells you what to look for. Geometry will never replace analysis, but geometry will tell you, look there, not the last inequality that I dreamt for breakfast. That's not going to do it. Geometry will tell you what is the correct variable and what kind of estimate you need. And I learned this the hard way myself in liquid crystals. Thank you very much.